to that. Alright, so what we want to do today is to introduce you to a new concept, one you wouldn't have seen before. So far, when you talked about models of the atom, we talked about this yesterday, I think in class, didn't we? We started going back to configuration. We spoke about how electrons are arranged around the nucleus of an atom, and we've used this model before. Okay, we called this electron shells, or we did start talking about the idea of clouds. Okay, so we've used that word maybe from Year 9, where we've introduced the idea of a cloud. Anyone know why we've actually used the concept of a cloud? Cloud. Mud. The electron doesn't have a definite place. It sort of does have a definite place, but you should be aware that electrons move around the nucleus very, very fast at the speed of light. So if I were to use an electron microscope to look at an individual atom, which you can do, I can't actually see electrons. Like, they don't actually go in nice concentric orbitals, and I can't say, for example, oh, there's the electron there, and there's the electron there. Okay, that's not how it actually works. However, we use this model, okay, we use that model when we go further into bonding in a few weeks' time. Okay, so that's but still not a model that we disregard, it still works, and it still is applicable for all the stuff we do on bonding when we talk about things like stable octet and why elements want to stable at a number, stable at a shell number. So that's the model of the electron distribution in an atom that we've done already. That's pretty straightforward and simple. We want to now go forward, okay, a few years. All right, this is the most recent model. Okay, it's called Bohr's model of the atom, and hasn't been a significant amount of change, all right, in many years in terms of the structure of the atom. But this is the most recent and the most up-to-date one. And when I did Year 12 Chem, this is what I looked at. So there's been no change since then. Okay. All right. So we want to introduce you to the idea of an orbital. So we use electron clouds and shells. We're now going to change that terminology, and we're going to come back and look at or introduce you to orbitals. This used to be in the Stage 2 course, okay, which is Year 12 Chem. It's now moved down to Stage 1. Okay, concept you should be able to understand relatively easily if you pay attention as we go through it. All right. So basically, what we're saying is, around the atom there are electrons. Or around the nucleus, I should say, there are electrons. The concept of them existing in shells is correct, but we want to move away from shells because this guy called Bohr actually worked out that they really exist in energy levels. And Mr. Elliot, if you've got Mr. Elliot for physics, okay, at Stage 2, just talk about the atom in lots, significant amount of depth. And so we now talk about electrons that don't exist in shells. Essentially, they're in areas around the nucleus. Those areas are called orbitals, and depending on where we find the electron is of a different energy level. We call that the Bohr model of the atom. And your assessment coming up looks at different models of the atom. Okay. Now, I've drawn on the board a three-dimensional axis because it's pretty obvious that atoms exist in three dimensions. It's not a two-dimensional arrangement. This model here looks at a two-dimensional arrangement. Okay, we've got a nucleus, we've got electrons that orbit the nucleus in a nice circle. They actually orbit the nucleus, okay, in a three-dimensional arrangement. So what I've got here are X, Y, Z axis, three dimensions. In the middle, okay, for each one of these, we've got the nucleus of the atom. We're not going to focus a lot on the nucleus. We know about atomic number, we know about mass number from yesterday's lesson. So you all should be aware that, you know, if we've got an atomic number of 19, if it's neutral, we're going to have 19 protons in the nucleus and a certain number of neutrons. So we're not going to go back over that. All right, so the nucleus is in the middle of each one of these models. So I've actually progressively built up, okay, the structure for the atom, showing you various types of orbitals. Now, the first type of orbital that we will be looking at is called an s orbital. It's lowercase s. It's given the symbol S. Just like we had K, L, M and N, or 1, 2, 3, 4. In orbitals, we use S, P, D, and F. And you work out within each one of those subshells, okay, so I've used the new term already, but within each one of those subshells there are a certain number of orbitals. I'll put on the board up here, we only can get 2 electrons inside of any individual orbital. So if I'm looking at over here the s orbital, I can only get 2 electrons in there. Now I put 2 dots there, but of course it's not like that, okay? It's just this cloud. Somewhere in there, around the nucleus, there are 2 electrons, and those electrons are in an s orbital. They're close to the nucleus and they're low energy. So s orbitals are always going to be sphere in shape. Everyone cool with that? So that's the first sort of orbital, s orbital. So if I've got 1 electron, it's going to be in the s orbital. If I've got 2 electrons in any element, it's going to be in the s orbital. Okay, there is another s orbital called the 2s orbital that we'll talk about in a minute. So outside of that, the next energy up, which I haven't drawn, would be another s orbital. It's slightly larger than this one, and we call that the s2, or the 2s. And somewhere in there are 2 more electrons, which are going to overlap the 1s, okay? Obviously, because they can move freely in that general area. So we call that the s subshell. There are 2 s orbitals. There's a 1s and a 2s, okay, within the s subshell. Then over here, this looks a bit complicated, but we move from there. If we've got more than 4 electrons in an element, then the electrons jump up to another energy level. The next energy level is called, what's it called, Harrison? P, all right? He's got a brother at university, all right, so that's probably going to help him. All right, P. Again, it's lowercase p. This is called the Py orbital, and it should be lowercase actually, they're all lowercase. That's which goes right along the y-axis. Then there's one called the Px orbital, which goes on the x-axis. And there's one called the Pz that goes on the z-axis. Now, if they're all filled, if the P subshell is filled, all 3 P orbitals are filled, I would have 2 electrons in that one, somewhere, 2 electrons in this one, somewhere, and 2 electrons in the X, okay, Px orbital as well. So a P subshell can contain up to 6 electrons. 3 orbitals, 2 in the first orbital, 2 in the second, 2 in the third. Okay? So S can only accommodate 2, an S subshell. A P subshell can have up to 2, 4, 6 electrons. Okay? And then there is a D. Now I'm not going to even attempt to draw the D. Okay? There are 5 D orbitals in the D subshell. You can look them up. The shape of them is very complex. Okay? So in the D subshell, 5 D orbitals, how many could we fit in a D subshell? If there's 5 orbitals? 10. 2, 4, 6, 8, 10. I think we've got 5 fingers on each hand, alright? So there's 5 D orbitals in the D subshell. We'll show you how to fill these up in a few minutes. There's also an F. So this is S, P, S is less than P, less than D, less than F, and it's just lowercase f. The maximum number, okay, we can accommodate in any S is 2. There's going to be 6 here because there are 3 P orbitals in the P subshell. And the D, we can go up to 10. There's 5 D orbitals. And up to, in the F, there are 7. We can go up to 14 electrons. So 7 orbitals, 2 electrons in each orbital. In total, up to 14 electrons. Everyone okay with that? Okay. So therefore, once we start off with a simple atom, okay, we build it up. So we fill up the s orbital first. So we can only have electrons filled up from the lowest energy up to the highest energy. That's why we fill them up from the s. When that's filled, it goes to the p. When that's filled, it goes to the d. When that's filled, we go up to the f orbital. So things actually go from lowest to highest energy. Okay, so if we had an element, for example, that had all the s and the p filled up, I'll show you what the configuration looks like. It would look like this. It would be, try and choose a nice colour. It would be 1s2. The subshell is number 1, okay? 2s2. Subshell number 2. I'll show you how that relates to the shells over here in a minute. And then we would have 2p6. Subshell number 2, if it's filled, 3 p orbitals, 2 in each one, all filled. So this idea here, all right, is what we are working our way towards. So I could actually draw, not that you actually don't have to do that, but I could actually draw an atom with that configuration. What is the atom, by the way? Can anyone identify what that would be? Come here.
Sulfur.
Sulfur, let's have a look. So that's 6, 7, 8, 9, 10 electrons. Harrison? What is it? Fluorine, is it? Okay. Fluorine is element number 9. Neon. Okay. Can you shut the door, please? So it must be the configuration for neon. Now, for those of you who are thinking ahead, it would have had to be one of the noble gases because it's got a full complement of electrons in all of the orbitals.
Yeah.
It's full.
So
Everything's full. It's stable. We used 8 as being stable before. So here is the configuration for neon. We use the word configuration using orbital notation. So if I were to draw it in the 1s, it's got somewhere in there 2 electrons. That's the 1s orbital. In the 2s, in the second shell, out here somewhere, it's got 2 more electrons. And of course they're going to overlap with the p orbitals, as you can see. All right? That's why it's called a cloud, it's just a big blur. And there's got 6 electrons in the p orbital. The fact that it's got 6 means there must be 2 in this one, and then 2 in that one, and then 2 in that one. So all 3 p orbitals would have 2 electrons filled. Okay. How are we going with that? Questions? Don't want to go too fast. So, just to reiterate again, old system, shells. New system, orbitals. Difference, electrons now exist in energy levels. Okay? And the energy levels are called S, P, D and F. And all elements have got electrons arranged within that combination of orbitals. And we fill them up from lowest to highest. Okay. If we did the old notation, when I say, I'm going to use that word old and new, I should say this sort of configuration. So we've already identified, you've told me that this is the configuration for neon, isn't it? Neon, because it's stable. And neon is element number 10. So the configuration for neon, we'll just move it up to here. You just told me, or else I told you, it was 1s2, 2s2, 2p6. What was its old configuration? So how would you give the configuration using the old notation, which is the good old one over here? 2 and 8. So you would have said neon, 10, 2, 8. Now, we haven't actually changed the old notation, we've just rejigged it a little bit. Because I'll draw a line down here. This is the first shell. First shell, it's got 2 electrons in it. This is the second subshell. We've got number 2 there. It's got 6 plus 2, it's got 8 electrons in it. So its configuration hasn't changed, it's still 2, 8. We've just moved the electrons into orbitals now. Okay, questions about that one? Okay, next step. So I just threw out there 1s2, 2s2, 2p6, etc. Unfortunately, the textbook doesn't have an order of orbitals. Some people might choose to learn this off rote, okay? When I did chemistry a long, long time ago, and when you look this up, you'll find that there are two methods of working out the sequence of orbitals, okay? This is the method that I've used, but you don't have to use this one, but it's easy. I'm sort of okay with this one. You need to copy this down exactly as it is. Otherwise, if you copy it wrong, every sequence of any atom that you do from now on is going to be wrong. Okay? So, these are the subshells. There's 7 subshells in total. And I'm going to show you the sequence of orbitals. And then I'll show you how we join those sequences together. Okay, now, we're never going to, I don't think you're ever going to be asked to do a configuration for element number 106. Typically though, you should be able to do the first 30 elements. First 30, okay, in orbital notation. But if you can do the first 30, I could give you any element and its atomic number, and you should be able to put it into orbital notation. Okay? So, why do you know the sequence of orbitals? So it goes like this. So 1s is the first orbital, 2s is the next energy up. Then it goes to p, and then it goes over to 3s, and it goes to 3p, that's still in shell 3. Then it's a bit weird, it goes down to 4s, and then it goes up to 3D, and then it goes in 3D, 4P, 5S. From 5S it goes back up, 4D, 5P, 6S, and then it goes all the way back up to 4S, 5D, 6P, and we won't even bother going any further, because you're never going to use it. So the sequence of orbitals is given here for you. That's what you have to learn. You've got to commit that to memory. You don't get that on a piece of paper in an exam. Or you get the periodic table and the activity series of metals. That you have to learn. Commit it to memory. Okay? When you do year 12, if you get to year 12, there will be some questions on orbital notation in the exam, because it's assumed knowledge. You would have done it at stage 1. Okay, so the sequence would be this. 1s, 2s, 2p. So I'm just reading. 2s, 2p. 3s, 3p. 4s, 3d. 4p. 5s, ... Stop there. Now some people learn that by heart. They learn that sequence off like that. I prefer that, because I'm a visual learner. I've got something to work from, okay? It's easy. It saves my brain from working too hard. So I just copy the sequence from the picture. That's how I work. Alright, so that's the sequence of orbitals, okay? 2 more things we are going to have a look at, okay? And I've just got to peel off some of that. Now, so if I look at a more complicated atom, okay, I had potassium on the board a minute ago and I just got rid of it. But let's say we did the configuration, the orbital notation for potassium, okay? And I want you to put it into orbital notation, and then we're going to draw an energy diagram for it, okay? Which is basically this in an energy level diagram, okay? From lowest energy to highest energy. I'm going to show you 3 ways of doing orbital notation that you have to be familiar with, okay? Alright, so we're going to do potassium, and it's element number 19. Okay, so we'll know that that's the atomic number. So now we've just got to go through and fill up all of the orbitals in the sequence with its electrons. And I'll just have to count. So it is 1s2, that's 2 electrons. Okay, 2s2. That's used up 4 of them. 2p6. So that's the second shell now. So we've got 2, 8 so far. Then we've got 3s2. We're up to 3s because you wasn't about. Yep, I'm up here. 3s2. Do I need to have the p filled? I think I do, don't I? 3p6. Yeah, I think we do. And then. So I've got 6, that's 10, 10 and 8, that's 18. I need to account for 1 more electron, so I have to go up to the 4s orbital, 4s1. Okay? So that's the electronic configuration using orbital notation for potassium. Remember, in the old system, it would have been 2, 8, 8, 1. It still sits behind this orbital notation. It's got 4 shells, 2 in the first shell, 8 in the second, 8 in the third, 1 in the fourth. Okay, we've separated the shells out into orbitals. Okay. What I'm going to do now is I'm going to draw little boxes to indicate the orbitals. So this would be an orbital. There's only, in the S subshell, there's only 1 s orbital. Here, same. But the P, in the P there are 3 orbitals. So this corresponds to Px, Py and Pz. This is another s orbital, so there's only 1 of them. S is a sphere, okay, and I can only fit 2 in that. Now we're up to another p orbital. There it is there. Okay, there's 3 of them. Px, Py, Pz. And then I've got another s orbital, so it looks like that. Now what I'm going to do, the next level of understanding is we're going to put the electrons in. Now, electrons travel in pairs, okay, and electrons are actually spinning. They spin in opposite directions. Okay, so how do I know? Because some smart scientists worked that out using quantum mechanics. Okay, so we've actually known that now for many years. That's how electrons move. They move in pairs and they move with opposite spins. We show it like this. In a picture, we look at it like this. So this represents an electron with a certain spin. If I wanted to show what's the opposite, well, here is another electron going in the opposite direction. That's the notation that we use, okay, at this level. And you'll see that when you go to tertiary level as well. Okay, so I'm going to fill them up. 2 electrons there. There's 2 electrons in here, there's 2 here, and there's 2 here. That's all full. All the 2p is filled. I'll run through it again in a minute, so don't worry about it, and you can watch it 1,000 times. Next one's filled. 3s is filled. Over here, the 3p has got 6 electrons in it. There it is, but the 4s has only got 1. Now it doesn't matter whether you do it like that, or you do it like that. There's only 1 of them in there. Okay? So that's only half filled. That orbital is only half filled. Alright, so that's the notation for potassium. using orbital notation, but I was told you I was going to do it 3 ways. Number 1 is the straight sequence. Number 2 is the picture of what it looks like when we put them into orbitals. And the third method is what we call the energy. So how do the electrons fill into the orbitals? And there's various diagrams that you'll see that will show you that. For example, this might be the 1s orbital. This could be the 2s. Okay, and then up here somewhere we've got the, whoops, try that again, the 2p orbital. Then somewhere up here we've got the 3s, and then up here we've got the, what are we up to, 3p orbital, and then up here somewhere we've got the 4s. So that's a very rough diagram, you'll see it in the textbook, okay? But it sort of shows the sequence of energy of orbitals from lowest to highest. Now, same thing, if I put the electrons in, there must be 2 electrons sitting there in the 1s. Then the 2s has got also 2 there. 2p, the 6 of them. 1, 2, 3, 4, 5, 6. Just copying from there down to my energy diagram now. 3s, there's 2. Again, there's 6 up here, and then the 4s is just 1. So that is the energy sequence of electrons for potassium. You've got to be able to do that for every element up to element number 30. Okay? Every element up to 30. Alright, now, the next thing we want to be able to do, alright, we've got the sequence of orbitals. I'm going to introduce you to another word, because we're sort of moving on with our course. And the word that I want to talk about is something that might have been mentioned last year. It's called the ground state. Ground state typically is stable, and it's the lowest energy for potassium. So if I went to get a piece of potassium out the back, even though it's not very stable, okay, this would be the lowest energy configuration for potassium. Okay, we call it ground state. Ground meaning it's basically the lowest energy it can exist in. Okay? Lowest energy. Mark, you get the door and just tell those guys to just wait for a second. So basically it's the lowest energy that we have, okay, for, in this case, potassium. 90% of the stuff we're going to be doing will all be lowest energy, okay, at this point, until we start talking about excited states. And for those of you that are thinking again a little bit forward, maybe I'll just stop there. So an excited state is where we begin to move electrons around. And the way that we move electrons around is through exciting them. And the way we excite electrons is normally by heat. Okay? So if we heat potassium, we can cause the electrons to go up to another energy level. It's not stable, so the excited state is unstable, but it's like a fingerprint for potassium. So if I have got potassium, and if I excite potassium, it'll give off a certain colour. Remember you did flame colours last year? So I know that potassium is going to be what colour? Potassium will always give it's going to be a white or yellow flame. Copper will give greeny blue. Okay? Strontium will get that nice crimson colour. Right? So this will give a certain colour based on where the electrons get moved to. That's a fingerprint for the element. It is always the same. It never changes. Okay, I'm going to stop that there. That's enough for you to digest, I think, in one session.